Every person who has ever heard about the Big Bang eventually arrives at the same small question, almost without meaning to. What was there before it? It feels like the most reasonable thing in the world to wonder, the obvious next step, a simple matter of looking far enough back. But hidden inside that question is an assumption so quiet that almost nobody notices they are making it. You are taking for granted that there was a before at all, an empty stretch of time already running, patiently waiting in the dark for the universe to switch itself on. And here is the part they rarely tell you. Our best theory of the beginning does not actually describe the beginning. Push the equations back toward the very first instant and they collapse into infinity, which is the sound a theory makes when it has reached the edge of its own validity. The moment of creation everyone pictures is the one moment our physics leaves blank. So the real question tonight is not what came before time, it is whether before was ever a real direction to travel in at all. Settle in and hit subscribe if you are new here, because by the end of this, the word before will never feel quite so solid again, and the beginning of everything will sound less like a settled fact and more like the most honest question we have ever asked. Now, let's slowly ease into this. Part 1. The question you have been asking wrong. There is a question that almost everyone arrives at sooner or later, usually late at night, usually after someone has explained that the universe began about 14 billion years ago in an event we call the Big Bang. The question comes out almost on its own, and it always sounds the same. What was there before? It feels like the most reasonable thing in the world to ask. If something started, then surely there was a moment just before it started, and a moment before that, stretching back into some kind of darkness that was patiently waiting for the universe to switch itself on. We ask the question with complete confidence, because the answer feels like it should simply be a matter of looking far enough back. Pay attention to what your own mind does when you try to obey the instruction to picture the very first moment of time. You summon up a dark, quiet emptiness, and then a flash, and you call the flash the beginning. But look carefully at that mental movie, because there is a cheat hidden in it. The dark, quiet emptiness came first. You placed a stretch of waiting, a kind of patient nothing, in front of the flash, and that waiting is already time. You did not imagine the beginning of time at all. You imagined a moment of time with an earlier emptiness in front of it, because that is the only kind of beginning you have ever experienced. Every beginning you know, a birth, a sunrise, the first note of a song, happens against a background that was already there. The mind reaches for that template automatically, and the template is exactly what fails when the thing beginning is time itself. This is why I keep insisting we separate the two questions, because the confusion between them is not a small slip, it is the whole trap. The question that has a hope of an answer is not what happened in the empty time before the beginning, because that question has already smuggled in the very thing we are trying to ask about. The question worth asking is whether there was any before at all, whether the dimension of time has a far edge or rounds off or runs on forever. And that question cannot be answered by imagining harder. It can only be answered by following the physics into the place where imagination gives out, and then trusting the mathematics to keep walking after our intuition has sat down in the road and refused to go any further. I want to slow down on that question tonight, because hidden inside it is an assumption so quiet that we almost never notice we are making it. When you ask what came before the beginning, you are taking for granted that there was a before at all. You are imagining time as a kind of empty road that already existed, running back past the moment of the Big Bang into an earlier stretch where nothing much was happening yet. You are picturing the universe arriving onto a stage that had been standing there, dark and ready, since forever. And that picture, as natural as it feels, may be the single most misleading idea a person can hold about the cosmos. Because here is the possibility that modern physics keeps circling back to, the possibility this whole video is about. The road might not be there. the stage might not exist. When you ask what came before time, you may be asking a question shaped exactly like a real question, made of ordinary words arranged in the ordinary way, that nevertheless points at absolutely nothing. Not nothing in the sense of empty space, nothing in the sense of a destination that was never on the map to begin with. Think about a different question for a moment, one that sounds almost as reasonable. What lies 1 mile north of the North Pole? You can say those words. They are grammatical. They have the same shape as what lies 1 mile north of my house, which has a perfectly good answer. But stand at the North Pole and try to take a step north, and you cannot do it. Every direction you can possibly walk is south. There is no north of the North Pole. Not because something is blocking the way, not because there is a wall or a cliff or a sign telling you to turn back, but because the word north has simply run out of places to point. The question feels like it should have an answer, and it does not. And the reason it does not is built into the shape of the world rather than into any lack of information on your part. The unsettling proposal at the center of this entire subject is that before time might be exactly like north of the North Pole. That when you trace the moments backward, one after another, toward the very beginning, you do not arrive at a first moment with an empty waiting room in front of it. You arrive at a place where the word before quietly stops meaning anything at all. And if that is true, then the question that feels so obvious, the question we all ask, was never really a question about the universe. It was a question about the limits of our own imagination. I should be careful here and separate two things that ordinary language jams together, because the entire video depends on keeping them apart. The first idea is what happened before the Big Bang, and that idea assumes time already runs backward past the beginning into some earlier era. The second idea is much stranger and much more precise. It asks whether time itself had a first instant. Whether the dimension we measure with clocks, the thing we move through from breakfast to midnight, has an edge, a boundary, a starting line, the way a ruler has a first millimeter and nothing to the left of it. Those two ideas are not the same, and nearly all the real physics, all the genuinely mind-bending parts of this story, live inside the second one. Notice what happens to the first question if the second one turns out a certain way. If time had a true first instant, then there was no before for anything to happen in, and the question of what came earlier does not get answered, it gets erased. There is no earlier, the word has nowhere to land. On the other hand, if time had no first instant, if it rounds off smoothly without a starting line, or extends backward forever into some prior phase, or turns out not to be a fundamental feature of reality in the first place, then the answer is stranger still, and we are going to spend the next while pulling each of those possibilities apart. What I find remarkable, and what makes this more than a game with words, is that this is not a new puzzle invented by physicists with their equations. The question of whether time could have a beginning has been quietly breaking the smartest minds in every century that bothered to take it seriously. A bishop in North Africa wrestled it to the ground 1600 years ago and came away with an answer that sounds like it could have been written last week. A philosopher in the 1700s proved, with what looks like airtight logic, that time must have had a beginning, and then proved with equally airtight logic that it could not have, and took that contradiction as a warning that human reason had wandered somewhere it was never built to go. And in the last 100 years, the physics finally caught up to the philosophy, and the equations that describe the beginning of the universe did something nobody quite expected. They did not reveal the first moment of time, they made the first moment disappear. So tonight we are going to walk all the way to the edge of time, as close as physics can take us, and we are going to look at what happens to the idea of before when we get there. We will find a wall made of fog, a stretch of the universe where time starts behaving like space, and a proposal from one of the most famous scientists who ever lived, that the beginning of everything is shaped like the bottom of the world. By the end, I do not think the question will be answered, Exactly. I think something more interesting will happen to it. I think it will dissolve in your hands, and you will be left holding something far stranger and more beautiful than an answer. But to get there, we have to start with the man who saw all of this first, long before anyone had measured a single receding galaxy, working by candlelight and pure reason alone. Part 2. A bishop beat us by 16 centuries. Long before there was a Big Bang theory, long before anyone had a telescope capable of proving the universe was expanding, the sharpest version of tonight's question was written down by a man with no equipment at all except his own mind. His name was Augustine, and around the end of the 4th century, somewhere close to the year 400, he sat down to write a book we now call the Confessions. And in one section of it, he turned to a problem that had clearly been needling him. If the world was created, then what was happening before it was created? What filled all that empty time before the first day? What strikes me most about Augustine's move is its sheer nerve, because he refused the easy exits that were available to him. He could have said the before was simply unknowable, a mystery reserved for the divine, and left it there. He could have taken the mocking joke that the heavens were busy preparing punishments for the curious, and used it to shut the conversation down. Instead, he did the harder and more honest thing. He examined the question itself, turned it over, and found that the flaw was not in our ignorance, but in the question's own construction. He located the error inside the words rather than inside the gap in our knowledge, and that is precisely the diagnosis modern physics would arrive at by a completely different route 1,500 years later. There is something humbling in realizing that a man with no instrument more powerful than careful thought could reach the doorstep of an idea our supercomputers and particle accelerators are still struggling to walk through. It tells us that this question is not really a technological problem, the kind you solve by building a bigger machine. It is a conceptual problem, a knot in the way thinking creatures relate to time, and bigger machines only bring you to the same knot faster and with more precision. Augustine arrived on foot, by candlelight, and found the knot already waiting. We arrived in a spacecraft of mathematics, and found the same knot, tied in the same place, refusing to come loose. He even records the mocking version of the question, the one skeptics threw at believers to embarrass them. What was God doing, they asked, in all those endless ages before he made heaven and earth? And Augustine notes, with a kind of dry humour, the cheap answer that some people gave, that God was busy preparing torments for people who ask questions that pry too far. He refuses to give that answer. He says it would be easy to deflect the question with a joke, but he would rather actually face it. And what he says next is the thing that gives me a chill every time I read it, because a man 1,600 years ago, with no physics whatsoever, reached almost exactly the conclusion our most advanced theories keep dragging us toward. Augustine argued that there was no before. Not that the before was empty, not that nothing interesting was happening in it, but that it did not exist. His reasoning was that time itself is part of the created world. Time is not an empty stage that was standing there waiting. Time came into being along with the changing, moving, unfolding world, because time is nothing more than the measure of change, and where there is no change, there is no time. So to ask what happened before the world began is to assume there was a then when there was no then to be had. The question, he said, contains its own mistake. There was no time prior to time. There was no moment before the first moment, because moment is a thing that only exists once the universe is running. Strip away the religious framing. Set aside whatever you do or do not believe about a creator, and look only at the structure of the idea, because the structure is what matters here. Augustine is saying that time might not be a container the universe sits inside. Time might be something the universe brought with it, generated, produced as it came into being. And if that is true, then before the universe is not a place you could ever travel to, because travel requires time, and there is no time outside the thing that makes it. He arrived, by reasoning alone, at the same suspicion that would later break our equations. There was no then when there was no time. Hold on to that phrase. We are going to come back to it later, when it deepens into something Augustine could never have imagined. What I love about this is that it tells us something important about the question we started with. The reason what came before the beginning feels so obvious and so unanswerable at the same time is not that we are missing a piece of data. It is not that we just need a better telescope or a faster particle accelerator, and then we will finally see into the prior era. The difficulty is older and stranger than that. It is built into the way human beings think about time. We are creatures who experience one moment after another, who are constitutionally incapable of imagining a state of affairs with no before attached to it. Ask a person to picture the very first moment of time and watch what their mind does. It immediately sneaks in a moment just before, a dark, quiet instant of, and then it began, because that is the only way we know how to think. There were, of course, thinkers who went the other way entirely. Aristotle, centuries before Augustine, had argued that time could not have had a beginning at all, that the universe was eternal, that it had simply always existed, with no first moment and no creation. His reasoning was almost the mirror image of the puzzle. For any moment you name as the first, you can always ask what came just before it, and the very fact that you can ask seems to prove there was an earlier time. So time, on this view, must stretch backward without end. Two of the greatest minds of the ancient and late ancient world then looked at the same question and came to opposite conclusions. One said, time must have begun with the world. The other said time could never have begun at all. And neither of them could deliver a knockout blow, because the question sits in a place where ordinary reasoning starts to fight itself. That standoff is worth sitting with, because it is the first hint of something we will see again and again tonight. Every time human thought approaches the beginning of time, it splits in two. One half insists there must have been a first moment. The other half insists there could not have been. And both halves can build arguments that sound completely convincing. This is not the signature of a problem we simply have not solved yet. This is the signature of a problem where our basic concepts, the very ideas of before and after, and beginning, may be breaking down underneath us. The way a tool designed for one job shatters when you force it to do another. Augustine could only take the question so far. He had insight, but he had no way to test it, no way to look at the actual beginning of the actual universe and check whether time really did smooth away into non-existence or whether it ran on backward forever. For that, the question had to wait 1,500 years until human beings learned to read the history of the cosmos in the light of distant galaxies and in a faint hiss of radiation filling all of space. And when they finally did look back toward the beginning, with real instruments and real mathematics, they found something that Augustine would have recognized instantly. They found that the theory describing the beginning of the universe stops working at exactly the beginning of the universe. They found a wall. And to understand why that wall is there and what it is really made of, we have to look closely at what the Big Bang Theory actually says, and at the one thing it quietly refuses to describe. Part 3. The theory of the beginning has no beginning. Let me clear away a misunderstanding that sits at the root of almost every confused conversation about the start of the universe, because once you see it clearly, the whole subject rearranges itself. When most people picture the Big Bang, they imagine an explosion, a single bright point sitting in an immense darkness, and then a detonation, matter flying outward into the empty space around it, the way a firework bursts against a night sky. It is a vivid image. It is also wrong in nearly every detail, and the ways it is wrong are exactly the ways that matter for tonight. Hold on to one more consequence of this, because it dissolves a question people often ask next. If the Big Bang happened everywhere, then it is not a place we could ever build a powerful enough rocket to visit, a smoking crater somewhere out past the farthest galaxies. The beginning is not a location in space that we are now far away from. It is a moment in time that we are now far away from, and those are entirely different kinds of distance. You cannot travel to the Big Bang any more than you can travel to last Tuesday, and no telescope, however large, will ever show it to us as a spot on the sky, because it is not a spot on the sky. It is the earliest page of the history of every spot on the sky at once. It helps to push the misconception all the way out of your mind by asking the one question of the explosion picture cannot survive. If the Big Bang was an explosion, where did it happen? Point to the spot. The honest answer is that it happened everywhere, because everywhere that now exists was, back then, the same tiny region. The place where the Big Bang occurred is not somewhere far across the cosmos that we could in principle travel back to. It is here, where you are sitting, and also in the most distant galaxy our telescopes can find, because all of those places were the same place when the universe was young. The expansion did not push matter out into a room. It stretched the room itself, and every point in the room remembers being the center. There is a further subtlety worth holding, because it sharpens the whole question of a beginning. When we say the early universe was unimaginably small and dense, we mean the part of it we can now see, the observable universe, was compressed into a tiny volume. We do not actually know whether the universe as a whole is finite or infinite. It is entirely possible that space was already infinite at the earliest moments we can describe, simply infinitely denser and hotter than it is now. An infinite universe does not start as a point and grow. It starts infinite and gets less dense everywhere at once. That possibility quietly reshapes the question of the beginning, because an edge in time is a very different thing from an edge in space, and we have been chasing the edge in time, the first moment, not a first place. The Big Bang was not an explosion in space. It was an expansion of space. There was no surrounding darkness for anything to fly out into, no empty room with the universe detonating in the middle of it. Instead, space itself was stretching everywhere, all at once, growing larger with every passing instant, and carrying everything along with it. The galaxies are not pieces of debris rushing away from a central blast site. They are more like raisins in a loaf of bread that is rising in the oven, drifting apart from each other, not because they are moving through the dough, but because the dough between them is swelling. There is no center to this expansion. Stand on any galaxy you like, and you will see all the others receding from you, and your neighbor on a distant galaxy sees exactly the same thing about you. Everyone is at the center, which is another way of saying no one is. Now we can run the film backward, which is exactly how the theory was built. If space is expanding today, getting larger and emptier and colder as the eons pass, then in the past it was smaller, denser, and hotter. Push the rewind far enough, and the galaxies merge back together. The atoms break apart into a glowing plasma, and the entire observable universe collapses into a state of unimaginable heat and density. Our best theory of gravity, Albert Einstein's general theory of relativity, handles this backward journey beautifully across an enormous range. It describes the cooling, the forming of the first atoms, the forging of the lightest elements, the soup of fundamental particles, all of it with a precision that has been confirmed against the actual sky again and again. This is one of the most successful pieces of science humanity has ever produced. But watch what happens as we push all the way back toward time zero, toward the very first instant. The equations say the universe was smaller and hotter and denser at every step backward, and they do not stop saying it. As you approach the beginning, the density the equations predict climbs higher and higher, and the temperature climbs with it, and neither of them levels off. They keep going up. And right at time zero, the mathematics delivers a result that is not a number at all. It says the density was infinite. It says the temperature was infinite. It says, the entire universe was crushed into a single point of zero size and endless heat. Here is the thing you have to understand about infinity in physics. When a physical theory hands you an infinity, it is almost never telling you that something in the real world is actually infinite. It is telling you that the theory has broken. An infinity is the sound a theory makes when it has been pushed past the edge of the territory it was built to describe. It is the equation throwing up its hands. So when general relativity predicts an infinitely dense point at the beginning of time, the right way to read that is not the universe really was an infinitely dense point. The right way to read it is general relativity has stopped describing reality here and started describing its own failure. Physicists have a name for this kind of breakdown point. They call it a singularity, and the singularity at the beginning of the universe is not a thing that exists. It is a place where our description of things falls apart. In the 1960s and 70s, the mathematicians Roger Penrose and Stephen Hawking proved a set of results now known as the singularity theorems, and these theorems made the situation precise and, in a way, worse. They showed that under very reasonable assumptions, general relativity does not merely happen to predict an initial singularity in this one model, it generically demands one. Given the kind of matter and energy our universe contains, the theory, taken honestly to its own limit, insists on producing a singularity at the beginning, a point where its own equations cease to mean anything. So the theorems are not proof that a singularity is real. They are proof of something subtler and more honest. They are proof that general relativity, followed all the way to the start, predicts the moment of its own breakdown. The theory tells you, in its own language, exactly where it stops being able to speak. So consider what this means for the picture in everyone's head. The flash of creation, the first instant, the starting gun of the cosmos, the very moment people most want explained when they ask about the Big Bang, is precisely the one moment the Big Bang theory does not describe. The theory is a magnificent account of the aftermath. It tells you what the universe was doing, a tiny fraction of a second after the beginning, and a second after, and 1,000 years after, and 13 billion years after, all the way to the cup of coffee cooling beside you right now. What it does not contain, what it cannot contain, is the first instant itself. The trigger sits in the gap, just past the edge of where the equations still hold. And this is where the modern version of tonight's question is finally born. We have a theory that runs the universe back to a sliver of a second after the beginning with extraordinary accuracy and then hits a wall it cannot cross. Behind that wall is the answer to whether time had a first moment. Behind that wall is the truth about whether before means anything. We cannot see across it with general relativity, because general relativity, by its own admission, dies at the wall. To go any further, we need something more, some new physics that does not break where Einstein's theory breaks. And before we can even reach for that new physics, we have to confront a disturbing possibility that the philosophers saw coming centuries ago. The possibility that the very idea of a first moment, the thing we are trying to find behind the wall, might be a contradiction in itself. To see why, we have to meet the man who proved tonight's question is unanswerable, and then proved the opposite, and meant both. Part 4. How to prove it both ways. In 1781, a philosopher named Immanuel Kant published a book with the forbidding title of The Critique of Pure Reason, and tucked inside it is one of the most elegant traps ever set for the human mind. Kant was fascinated by certain questions that reason seems compelled to ask, but seems unable to answer, and he noticed that some of these questions had a peculiar property. You could build a convincing argument for one answer, and an equally convincing argument for the exact opposite answer, and both arguments would seem valid. He called these pairs antinomies, and the very first one he laid out is about precisely our subject. Did the universe have a beginning in time, or has it existed forever? The word Kant chose for these self-contradicting questions, antinomy, is worth keeping because it names something we will meet again and again at the edges of physics. An antinomy is not a paradox you can untangle with a clever insight, and it is not a simple mistake one side has made. It is a place where two lines of reasoning, each apparently sound, march straight into each other, and the collision tells you that something in the shared assumptions of both arguments is rotten. The way out of an antinomy is never to declare one side the winner. It is to find the buried premise that both sides took for granted, the assumption so obvious that nobody thought to question it, and to discover that this assumption is the real culprit. In the case of time's beginning, the buried premise is not hard to name once you go looking for it. Both of Kant's arguments, the one proving time began and the one proving it could not, quietly assume that time is a fixed, absolute backdrop, an empty container that either has a first moment or does not. Pull that assumption out, allow that time might round off or emerge, or not be fundamental at all, and the airtight arguments lose their grip, because they were never really arguments about the universe. They were arguments about a picture of time we carry in our heads, the picture of an empty, endless line, and the universe is under no obligation to match the picture. That, more than any single equation, is the permission slip the rest of this video runs on. It is the moment we are allowed to stop trusting the line. Let me walk you through both sides, because the experience of watching them both feel correct is the whole point. First, the argument that the universe must have had a beginning. Suppose it did not. Suppose that right now, at this moment, an infinite amount of time has already passed. That means an endless series of events, with no first member, has somehow been completed and delivered us to the present. But think about what it takes to complete an infinite series by adding one item at a time. You can never finish. No matter how long you count, you have only ever counted a finite amount, with infinitely more still to go. An infinity that has been fully run through, all the way to its end, is a contradiction, because infinity, by definition, has no end to reach. So, if the present moment has actually arrived, the past cannot be infinite. There must have been a first moment. Time must have begun. That feels airtight. Now, hold that feeling, and watch Kant demolish it with the opposite argument. Suppose the universe did have a first moment in time. Then, before that first moment, there was empty time, time in which nothing existed, stretching back. But here is the problem. One empty moment of time is exactly like any other empty moment of time. There is nothing to distinguish them, nothing that makes one of them special. So what could possibly explain why the universe began at that particular instant rather than a moment earlier or a moment later? In a featureless stretch of empty time, there is no reason for a beginning to happen here rather than there, and a beginning with no possible reason, no condition that singles out its moment, cannot occur. So the universe cannot have had a first moment. Time must stretch back without beginning. Both arguments are right there in front of you, and both feel like they work, and they cannot both be true. The universe either had a beginning or it did not. There is no third option, and yet reason marches you confidently to both conclusions. Kant's point, and this is the thing I want you to carry forward, was not that one argument secretly contains a flaw we just have to find. His point was that the contradiction itself is the lesson. When the mind produces a flat contradiction like this, calmly and rigorously, from premises that all seem reasonable, it is a sign that the mind has overreached. It has taken concepts that work perfectly well for objects inside the universe, ideas like before and cause and beginning, and tried to apply them to the universe as a whole, where those concepts may simply not hold. Think about what this is really saying, because it connects directly to the war we just hit with the physics. We found that general relativity breaks down at the first instant, producing an infinity that signals the theory has reached its limit. Kant is pointing at the same edge from the other direction, from inside pure thought, and finding that human reasoning breaks down at the first instant too, producing a contradiction that signals our concepts have reached their limit. Two completely different tools, the equations of physics and the logic of philosophy, both push toward the beginning of time and both shattering at the same spot in the same way. That is not a coincidence. That is two different instruments detecting the same crack in the foundation, and the crack is in the idea of the first moment. We have been assuming all along that the first instant of time is a coherent thing, a real, if hard-to-reach target, like a treasure buried somewhere we cannot dig. Kant is suggesting it might be more like a square circle, words that combine into a phrase that sounds meaningful but describes nothing that could possibly exist. If the very notion of a first moment is internally contradictory, then no amount of better physics will ever find it. For the same reason, no amount of better surveying will ever find the place 1 mile north of the North Pole. The thing we are looking for may not be hidden. It may be incoherent. Now, I do not want to leave you stranded in pure philosophy, because physics does not simply give up here, and neither should we. Kant was working with the only tool he had, human intuition about time, and that tool failed. But human intuition fails all the time in physics, and we have learned not to trust it at the extremes. Our intuition says nothing can be in two places at once, and quantum mechanics calmly violates that every day. Our intuition says time flows at the same rate for everyone, and relativity calmly violates that too. So the fact that intuition collapses at the beginning of time does not mean reality collapses there. It means we need to stop relying on intuition and start following the mathematics into the place where intuition cannot go, even when the mathematics says things that sound impossible. That is exactly what the next part of the story does. Because there is a specific point, a specific scale, where the smooth, sensible, intuitive picture of time as a steady stream of moments genuinely stops working, not as a matter of philosophy, but as a matter of physics. There is a duration so short that below it, the question, what happened in the instant before this one, loses its meaning, the way the question, what is the temperature of a single atom, loses its meaning. Physicists can calculate this scale precisely. It marks the boundary where Einstein's smooth spacetime and the jittery uncertainty of the quantum world collide, and where neither one survives. To go any closer to the beginning, we have to walk right up to that boundary and look at what time does there. So let us go to the wall, the real one, the one made not of philosophy but of physics, and let us stand as close to it as anyone can. Part 5. The wall at the bottom of the clock. Physics has a precise name for how close we can get to the beginning before the very language of time falls apart, and it comes from combining the three most fundamental constants in nature: the speed of light, the strength of gravity, and the quantum of action that governs the subatomic world. When you combine these three numbers in a particular way, they hand you a duration, a specific length of time, and it is called the Planck time. Its value is about 5.39 times 10 to the minus 44 seconds. I want to try to make that number mean something, because written out it is just a smear of zeros, and the meaning is where the vertigo lives. It is worth saying plainly that this wall is not a failure of effort or funding. It is not that we have not built a big enough machine yet, though bigger machines would help with many things. The Planck scale sits so far below anything we can probe directly that no conceivable experiment reaches it head-on. The energies involved are beyond any collider we could imagine building. So the fog at the bottom of the clock is not a temporary gap that next year's budget will close. It is a genuine frontier, a place we can approach only with mathematics and inference, never with a direct measurement, and that is part of why the beginning of time has kept its secret so well. The one event we most want to witness is the one event physically sealed off from any witness. To feel why both theories die at this scale, it helps to remember what each one assumes about the world. General relativity assumes space-time is smooth, a continuous fabric that curves gently like the surface of a calm pond. Quantum mechanics assumes that at small enough scales, everything jitters, fluctuates, refuses to hold still. For most of the universe, these assumptions never clash, because the pond is enormous and the ripples are tiny. But as you shrink toward the Planck scale, the ripples grow until they are as large as the pond itself. The smooth fabric of space-time is predicted to froth and boil, to tear and reconnect into what the physicist John Wheeler called a churning foam, where the very notions of distance and duration lose their footing. A smooth curved space-time and a violently fluctuating one cannot both be the truth at that scale, and the mathematics that would tell us which wins, or how they combine, is the theory we do not yet have. And notice that it is not only time that frays here, space frays with it. The same fog that swallows the meaning of the next moment also swallows the meaning of the next millimetre, because at the Planck scale, the ideas of here and there blur exactly as the ideas of before and after blur. This matters for our question, because it means we cannot rescue ourselves by imagining the beginning of time happening at some tiny point in space. There is no reliable point and no reliable instant down there. Only the foam, and the beginning of the universe is somewhere, or somewhen, inside it. Every road we have for thinking about the origin leads to this same shimmering boundary, and every one of them arrives without the tools to cross it. Consider the ratio between 1 second and 1 Planck time. That is, ask how many Planck times fit inside a single tick of a clock. The answer is a number with more than 40 digits in it. Now compare that to the number of seconds that have elapsed since the Big Bang across the entire 13.8 billion year history of the universe. That number of seconds has only about 17 or 18 digits. So there are vastly more Planck times in 1 second than there have been seconds in the whole age of the cosmos. The Planck time is to a single second, roughly, as a single second is to a span far longer than the universe has existed. It is almost unimaginably small, and it is the smallest interval for which our current physics can even pretend to speak of a before and an after. Why does time break down there, of all places? The reason is a collision between the two greatest theories we have, theories that everywhere else in the universe politely stay out of each other's way. General relativity describes gravity and large smooth things, planets, stars, galaxies, the gentle curvature of space-time. Quantum mechanics describes the small and the jittery, particles, atoms, the restless uncertainty that governs the tiniest scales. For almost everything, these two theories never have to talk to each other, because gravity is far too weak to matter for a single particle, and quantum jitter is far too small to matter for a planet. But at the beginning of the universe, everything that exists was packed into a region smaller than an atom, and at that size, the entire cosmos is both extremely massive and extremely tiny at the same time. Gravity and quantum mechanics are forced into the same room, and when they meet, they do not combine into a working description. They contradict each other. The smooth, continuous time of relativity and the probabilistic flicker of the quantum world cannot both be right at that scale, and we do not yet have the theory that resolves the conflict. Let me try to take you there, as close as words can manage, because this is the place where the abstract becomes something you can almost feel. Imagine you could count backward toward the beginning, instant by instant, riding the universe in reverse as it shrinks and heats. At first, it is steady. One moment, then the moment before it, then the one before that, a clean, orderly march into the past, each tick as solid as the last. The universe grows smaller and brighter around you, and still the clock ticks evenly, reliably, the way clocks are supposed to. You feel certain you could keep this up all the way to the start. But as you approach that final tiny fraction of a second, something begins to go wrong with the ticking itself. The intervals between moments stop being crisp. The boundary between this instant and the next one starts to blur, to smear, like ink running on wet paper. You reach for the next tick backward and find that there is no clean next tick, only a kind of grey shimmer where before and after refuse to fully separate. The clock in your hand is not slowing down, exactly. It is losing the ability to say which moment comes first. Try to ask what happened one Planck time earlier, and the question itself goes soft in your mouth, because at this scale, the universe does not seem to have a definite earlier, only a fog in which the order of moments dissolves. You have not hit a wall you could touch. You have arrived at the place where the very idea of the next moment stops working, where time has frayed into something our minds and our mathematics cannot yet follow. That is the real boundary. Not a barrier in space, not a curtain you could pull aside, if only you had a brighter light, but a horizon of meaning, a place where the concept of when gives out the way, the concept of north gives out at the pole. The beginning of the universe, whatever it was, sits on the far side of this fog, and the crucial thing to understand is that we did not run out of telescope. We ran out of time in the most literal possible sense. The classical idea of a steady stream of instants simply does not apply down there, and until we have a theory of quantum gravity that does apply, we are standing at the edge of the fog, peering in, unable to say what shape time takes inside it. For decades, this looked like a dead end, a permanent wall beyond which nothing could be said. But then a pair of physicists made a move so audacious and so strange that it took the rest of the field years to absorb what they had done. They asked what would happen if, right there in the fog, time stopped being time at all. If the reason we cannot find the next moment backward is that, near the beginning, the dimension of time quietly transforms into something else, something that does not have a next moment because it does not flow at all. It sounds like nonsense. It is, in fact, one of the most serious ideas in modern cosmology, and to understand it, we have to watch time turn into space. Part 6. When time starts acting like space. To understand the move that James Hartle and Stephen Hawking made in 1983, we first have to appreciate just how different time is from space in our normal understanding of reality, because their whole proposal hangs on erasing that difference. In everyday life, space and time could not feel more unlike each other. In space, you can move freely in any direction. You can go left or right, forward or back, up or down, and you can return to where you started. Space is the dimension of freedom. Time is the opposite. In time, you are dragged in one direction only, always from past to future, never able to stop, never able to turn around, never able to revisit a moment you have left behind. Time is the dimension of the prison. This asymmetry is so total that we rarely even notice it as a fact about the world. It just is the world. I want to reassure you that moving to imaginary time is not a desperate trick invented only to make the beginning of the universe behave. Physicists use it constantly in problems that have nothing to do with cosmology, because rotating a calculation into imaginary time often turns an impossible integral into a manageable one, and then you rotate the answer back into ordinary time at the end. It is a well-worn bridge that engineers and theorists cross in both directions every day. What Hartle and Hawking did that was bold was to suggest that, near the origin of the universe, the imaginary time description might not be a temporary bridge you cross and come back from, but the more truthful picture of what is actually there. They were proposing that the strangeness is not in the mathematics. The strangeness is in the beginning itself. The shape this produces has a name that helps it stick in the mind. The no-boundary universe, drawn in imaginary time, looks something like a badminton shuttlecock or a spinning top stood on its point, except that the point is not sharp. It is rounded, like the smooth bottom of a bowl. Travel up the wide part, and you are in the ordinary, expanding universe with ordinary, flowing time. Travel down toward the narrow part, and time gradually becomes space. The walls curve inward, and the whole thing closes off in a gentle dome, rather than ending at a spike. There is no rim, no lip, no first edge, anywhere on that smooth cap. You could run your finger over the entire surface and never cross a boundary, because there is no boundary to cross, only the place where the surface, like the surface of the Earth at the pole, has done all it can do. In the mathematics of relativity, this difference between time and space shows up as a single, stubborn minus sign. When physicists write down the geometry of space-time, the formula that measures the separation between two events, the 3 dimensions of space, all enter with a plus sign, and the 1 dimension of time enters with a minus sign. That minus sign is doing enormous work. It is the mathematical fingerprint of everything that makes time feel like time and not like another direction of space. It is why you can stand still in space, but never in time, why the future is unreachable until it arrives, and the past is gone once it passes. Now here is the trick, and it is a real and standard piece of mathematics, not a sleight of hand invented for this one purpose. There is an operation physicists use across many fields called moving to imaginary time. You take the time variable in your equations and you multiply it by the square root of -1, the imaginary unit. It sounds like an arbitrary thing to do, but in many areas of physics, it is a routine and powerful technique that makes hard problems solvable, and it has a remarkable side effect on the geometry of spacetime. When you express time as imaginary time, that stubborn minus sign turns into a plus sign, and suddenly, in the mathematics, time is no longer different from space. The formula treats all 4 dimensions identically. The prison dimension becomes just another direction of freedom. Time, in imaginary time, behaves exactly like space. Hartle and Hawking asked a daring question. What if this is not just a calculational trick near the beginning of the universe, but something close to the truth about what time does down there in the fog? What if, as you approach the very origin, time gradually loses its special character, its minus sign, and starts behaving like a 4th dimension of space? Then the picture of the beginning changes completely. Run an ordinary timeline backward, and it has to end somewhere, at a first point, a sharp edge, a singularity. But a space-like dimension does not have to end at a sharp edge. It can curve around and close up smoothly, the way the surface of a sphere closes up with no boundary and no edge anywhere on it. Let me bring you down into this, because it is one of the strangest things I have ever tried to picture, and the only way through it is to imagine it directly. Picture yourself traveling backward down the axis of time toward the origin of the universe, the way you might walk south across the curving surface of the Earth. For most of the journey, time is time. It runs in its single familiar direction. Behind you, the future. Ahead of you, the past. The one-way street you have always lived on. But as you get close to the beginning, you begin to feel the street change underfoot. The direction you are walking, the direction called into the past, starts to soften. It stops feeling like the one forbidden direction and starts feeling like simply one direction among several, the way south stops being special as you near the bottom of a globe. The rigid one-way arrow of time loosens, tilts, and begins to behave like a direction you could turn within, a direction with neighbors on either side, rather than a single track. Time is not ending ahead of you. Time is rounding off, curving, becoming spacious. There is no final instant waiting at the bottom, no edge to fall off, because the dimension you have been traveling has quietly become the kind of dimension that closes smoothly upon itself, like the curve of a surface with no rim. If your mind rebels at this, good. It should. We have no intuition for time behaving like space, because we have never experienced it and never will at the scale of our daily lives. But the mathematics does not rebel. The mathematics handles imaginary time as easily as it handles real time, and when you write the beginning of the universe in imaginary time, the singularity, that infinitely sharp point of breakdown, simply is not there. In its place is a smooth, rounded, finite cap, like the bottom of a bowl, like the southern tip of the world. The universe in this picture still has a finite past. It is not eternal. You do not get an infinite stretch of earlier time, but it has no first moment, no boundary, no edge, because the dimension of time smooths over into space before any first moment can occur. This is the very core of what is called the no-boundary proposal, and we are now standing right at its threshold. The idea is that the universe is finite but unbounded, finite in its past but with no edge to that past. In the same way, the surface of the earth is finite in area but has no edge you could ever walk off of. And once you accept that picture, the question we started with, the question everyone asks, undergoes a transformation. What came before the beginning stops being a hard question with a hidden answer and becomes something else entirely, something Hawking captured in an image so simple and so devastating that it has defined this subject ever since. He compared it to standing at the bottom of the world and asking what lies further south. To see why that image is so final, and why it might be the literal truth about the origin of everything rather than just a clever analogy, we have to follow the no-boundary universe all the way down to the pole. Part 7. South of the South Pole. Stephen Hawking spent the rest of his life returning to a single image to explain the no-boundary proposal, and it is worth understanding exactly why he chose it, because the image is not decoration. It may be close to the literal geometry of reality. He said that asking what happened before the Big Bang is like asking what lies south of the South Pole. Let me make sure that lands with its full weight, because the first time you hear it, it can sound like a clever dodge, and it is not a dodge. It is a precise claim about the shape of time. And there is one more honest thing to admit about the pole, which is that standing on it does not actually feel like an ending while you are there. The South Pole of the Earth is not a dramatic place. There is no abyss, no shimmering boundary, just more ice, more sky, the ordinary world continuing in every direction, all of them north. If the beginning of time really is shaped like that, then the first moments of the universe, whatever they were not marked by any sign saying this is the edge. The edge is only visible from far away, in the convergence of the lines, in the running out of a direction. From inside, it would have been simply the universe, being the universe, with no announcement that there was nothing earlier, because nothing earlier is not a thing that can be announced. There is a way to feel the strangeness of this in your own body, using nothing more exotic than a globe. Put your finger on the equator and slide it south. For a long while, south is a perfectly good instruction, and your finger obeys, moving steadily down the curve of the world. But as you near the bottom, something happens that you can watch with your own eyes. The lines of longitude, which ran parallel and proud across the middle of the globe, begin to lean toward each other, to converge, to crowd together, until at a single point they all meet and there is nowhere left to go. You did not hit a wall. The instruction simply completed itself and had nothing further to ask of you. That convergence, that gentle running out of a direction, is the closest thing in ordinary experience to what the no-boundary proposal says happens to time at the beginning of everything. I think the reason this idea unsettles people so much, more than black holes, or the size of the cosmos, or any of the other strange things in physics, is that it touches a need most of us did not know we were carrying. We need things to start. We are born, and that birth is a beginning we can point to. Every book has a first page, every song a first note, every day a sunrise. The expectation of an opening is woven so far into how we think that a universe without one feels almost like a violation. And yet that expectation is a habit of beings who live inside time, beings for whom every moment really does have an earlier one. Lifting that habit off the universe as a whole, allowing the possibility that the totality of everything simply does not have an opening the way its contents do, is one of the hardest and most freeing things the mind can attempt. Stand at the South Pole of the Earth. It is a completely real place. People have stood there, planted flags there, taken photographs there. It is not mysterious or hidden or forbidden, and yet there is no such thing as south of it. Every direction you can point from the South Pole leads north. The concept of south has not been blocked or hidden at that spot. It has simply run out, because south is defined by the curved surface of the Earth, and at the pole, that surface has done everything it can do in the southward direction. You do not reach the South Pole and find a wall with "no further south" written on it. You reach the South Pole and discover that further south was never a real place to begin with. It was a direction that the geometry of the globe allows only up to a point and then dissolves. Hawking's claim is that time, near the beginning of the universe, is shaped exactly like that. The Big Bang is not a wall standing in the middle of an earlier stretch of time. It is the pole. It is the place where the dimension of time, having become space-like and rounded in the way we explored, simply closes off. Asking what came before it is asking for a moment further into the past than the most past moment, and there is no such thing, not because something forbids it, but because past has run out of places to point. The question feels like it should have an answer, for the same reason south of the South Pole feels like it should have an answer. Our language lets us form the words. The world does not provide a referent for them. What I find genuinely moving about this idea is what it does to the search we have been on all night. We set out looking for the first moment of time, the trigger, the thing behind the wall. We treated it like a destination, a hidden chamber we just needed the right key to open, and the no-boundary proposal tells us that the search does not end in a discovery, it ends in a dissolving. You walk and walk toward the beginning, expecting to arrive at last at a door marked the first instant, and instead you find that the corridor curves gently back on itself, and there was never a door because there was never an edge for a door to sit in. The beginning of the universe, in this view, is not a moment when nothing became something. It is a smooth, rounded boundary that is not a boundary, a place where time is finite but has no first tick, the way the Earth's surface is finite but has no first inch. I want to sit with the feeling of that, because it is a strange braid of relief and unease, and I think it is worth letting yourself feel both threads. There is a relief in it. The question that has tormented thinkers for thousands of years, the question that broke Kant's logic and would not let Augustine rest, may have tormented us only because it was malformed. There may be nothing missing, no terrible empty before we have failed to explain, no infinite regress of earlier and earlier moments. The unanswerable question may have been unanswerable the way north of the North Pole is unanswerable, which is to say, not a real question at all. That is a kind of peace. But underneath the relief is something colder, and I do not want to pretend it is not there. We came looking for a first page, the opening line of the story of everything, and we are being told there may be no first page. Not that it was lost or burned, but that the book may have no edge, no cover, no beginning to its beginning. There is something vertiginous about that, something that pulls the floor out from under a need most of us did not even know we had, the need for things to start. Every story we tell has a beginning. Every life we live has a birth. We are built to expect openings. And the universe, the one thing that contains all stories and all lives, may simply not have one, not because of any deficiency, but because beginning, like before, may be a concept that does not survive contact with the edge of time. You went looking for the first moment of everything, and what you found instead was the quiet, dizzying possibility that first moment was a phrase your mind invented and the universe never honored. I should be honest about the status of all this, because intellectual honesty is the whole point of doing it carefully. The no-boundary proposal is not proven. It is a serious, mathematically detailed idea from two of the finest minds in physics, and it is also one possibility among several, resting on the use of imaginary time, and there is a genuine and unresolved debate about whether imaginary time describes literal reality or is a calculational tool that helps us compute things in the real, ordinary time we actually live in. Hawking himself was careful about this distinction at times and provocative about it at others. So, I am not telling you that this is how the universe began. I am telling you that one of our most powerful frameworks for the origin of everything does not find a first moment, and instead finds a reason the first moment may never have existed. That is a remarkable thing for a physical theory to say, and it should change how you hear the original question forever. But there is a deeper move still available, one that goes underneath even the no-boundary proposal and pulls the rug out from under it in turn. The no-boundary idea still treats time as real, as a genuine dimension that happens to round off near the origin. It assumes time exists, even if it has no first moment. What if that assumption is the thing that is wrong? What if time, the thing we have been trying to find the beginning of, is not a fundamental feature of reality at all? What if, when you look at the equations that govern the entire universe at once, time is simply not in them? That sounds impossible, and it is exactly what one of the central equations of modern physics appears to be telling us. To follow the question to its true bottom, we have to look at the equation that forgot about time. Part 8. The equation that forgot about time. For most of the 20th century, physics ran on two great theories that did not get along, and the dream of unifying them, of finding a single theory of quantum gravity that would describe both the very large and the very small, became one of the most important quests in all of science. We have already seen why this matters for the beginning of the universe. The fog at the Planck scale is exactly where quantum gravity is needed, and where we do not yet fully have it. But one early attempt to write down a quantum equation for the entire universe produced a result so bizarre that physicists are still arguing about what it means more than half a century later, and that result strikes directly at the question of time's beginning. To feel the force of the problem of time, picture the difference between a film and a single photograph. A film is a story in time. Frame follows frame, and the equation that describes it tells you how to get from one frame to the next. A photograph is a single frozen instant, complete in itself, going nowhere. Every equation in physics before this one had been like the rule for a film, a recipe for change. And then you write down the equation for the entire universe, expecting the grandest film of all, the story of everything unfolding, and what you get instead reads like the description of a single photograph. The cosmos, in this equation, does not play. It simply is one changeless frame, with no instruction anywhere inside it for what comes next, because, as far as the equation is concerned, there is no next. Physicists have not reached agreement on what to make of this, and the disagreement itself is illuminating. Some treat the missing time as a flaw, a sign that the equation is a crude first draft, and that the finished theory of quantum gravity will restore time to its rightful place at the center. Others, and this is the position that makes the subject so thrilling, treat the missing time as the most important discovery in the whole equation, a message we have been too attached to our intuitions to receive. On this reading, the equation is not failing to describe time. It is succeeding in describing a universe that does not fundamentally have any, and the burden falls on us to explain why, in that case, we feel time so overwhelmingly. That explanation is not a luxury. If the bedrock is timeless, then the flow we live inside has to come from somewhere, and finding its source becomes the central task. In the 1960s, the physicists John Wheeler and Bryce DeWitt wrote down what is now called the Wheeler-DeWitt equation. The The goal was straightforward in spirit, even if the mathematics is forbidding. Quantum mechanics has a master equation that describes how the quantum state of a system changes over time. Wheeler and DeWitt wanted to write the version of that equation that applies not to a single particle or atom, but to the entire universe, treated as one quantum system, with gravity included. When they did it, when they finally assembled the equation that governs the quantum state of the whole cosmos, they found something that stops you cold. The equation has no time in it. The variable for time, which sits at the very center of every other equation in quantum physics, telling you how things evolve from one moment to the next, simply is not there. It dropped out. Let me make sure you feel how strange this is. Every other fundamental equation in physics is, in some sense, a story about change over time. It takes the state of the world now and tells you the state of the world a moment later. Time is the spine of the whole enterprise. And then you write down the equation for everything, for the universe in its entirety, and time vanishes from it. The equation does not describe the universe evolving. It describes the universe simply being a single, static, timeless quantum state, frozen, with no next moment anywhere in the formula. Physicists call this the problem of time, and it is not a minor technical wrinkle. It is one of the most profound unsolved puzzles in theoretical physics, and people have built entire careers trying to understand what it is telling us. There are roughly two ways to react to an equation that says the universe does not change in time. The first is to suspect that the equation is incomplete, that we have made some error or oversimplification, and that the real, finished theory of quantum gravity will put time back where it belongs. That is a perfectly respectable position, and some physicists hold it. But the second reaction is far more interesting and, to many, more compelling. It is to take the equation at its word. To say that perhaps the equation is not broken, perhaps it is telling us a truth so counterintuitive that we have been reluctant to hear it. Perhaps time is not a fundamental feature of reality at all. Perhaps, at the deepest level, the universe really is timeless, a single unchanging quantum whole, and the flowing time we experience is not part of the bedrock, but something that appears at our scale, the way other familiar things appear at our scale, without being fundamental. This is less crazy than it sounds, because physics is full of properties that are completely real at one level and completely absent at another. Consider temperature. A cup of coffee has a temperature. It is hot, but a single molecule of water has no temperature. Temperature is not a property a lone molecule can have. It only emerges when you have enormous numbers of molecules jostling together, and it is really a summary of their average motion. Temperature is real. You can burn yourself on it, and it is also not fundamental. It is a large-scale pattern that arises from a deeper level where there is no such thing as temperature at all. The radical proposal on the table is that time might be like temperature, real at our scale, something we genuinely experience and measure, and yet not part of the fundamental description of the universe, emerging instead from some deeper, timeless structure, the way warmth emerges from molecules that are not themselves warm. Now look at what this does to tonight's question, because it goes even further than the no-boundary proposal did. The no-boundary idea told us that time is real but has no first moment, that before runs out like south at the pole. This goes underneath that. If time itself is not fundamental, then asking what came before time is malformed twice over. Not only is there no first moment of time to stand before, there may be no fundamental time for before and after to even be features of. You would be asking for a moment earlier than the earliest moment of a thing that, at bottom, does not consist of moments at all. Remember Augustine, 1600 years ago, saying there was no then when there was no time. This is that thought, pushed to a place he could never have reached. It is not only that there was no earlier time, it is that, then, the very idea of a moment may be something the universe produces rather than something it is made of. But this raises an obvious and pressing objection, maybe the most pressing one in this entire video, and if you are feeling it right now, you are in good company. If the universe is fundamentally timeless, if the deepest equation has no time in it, then why on earth do I feel time so vividly? Why does this moment so plainly give way to the next? Why do I remember the past and not the future? Why does my coffee cool, my body age, my life move undeniably forward? A timeless universe sounds beautiful and strange on a chalkboard, but I am sitting here experiencing the flow of time as the most obvious fact of my existence. How can both be true? How does a frozen, changeless cosmos give rise to the relentless river of time I feel carrying me along right now? The answer, or at least the most fascinating attempt at an answer, is that time might be a kind of relationship, something that exists not in the universe as a whole, but between its parts. And to understand that, we have to find the tick hiding inside the frozen hole. Part 9. The clock with no first tick. The most elegant attempt to explain how a timeless universe could give rise to the flowing time we experience came from two physicists, Don Page and William Wooters, in 1983, and the idea is so clever that once you see it, you cannot unsee it. They started from exactly the puzzle we just hit. The universe as a whole, according to the Wheeler-DeWitt equation, does not change. It is static. So where does our experience of change come from? Their answer was that time is not a property of the universe as a whole. Time is a relationship between one part of the universe and another part. Julian Barber gave the frozen snapshots a name that captures their self-sufficiency. He called the special configurations that carry the appearance of history time capsules, arrangements of matter that contain, frozen within them, what looks for all the world like records of a past. A geologist's rock with its layers, a photograph in a drawer, the memories laid down in your brain, the light from distant stars, arriving now but emitted long ago. Each of these exists complete in a single now, and each one seems to point backward to earlier moments. But in Barber's picture, the earlier moments are not somewhere the snapshot came from. They are simply other nows, equally frozen, and the sense that this one followed from those is a story the present configuration tells about itself, written into its own structure. Nothing flows from one to the next. The flow is read off the contents of each still frame, the way you can read motion in a single blurred photograph without anything in the photograph actually moving. Carlo Rovelli adds a further layer that I find quietly beautiful. He argues that the time we experience is bound up with our own ignorance, with the fact that we see the world in a blurred, averaged, coarse way rather than tracking every particle individually. Out of that blurring, out of the statistics of heat and disorder, a direction and a flow emerge that are perfectly real for beings like us, but absent from the fundamental description. Time, on this view, is not a cosmic river, and not even quite an illusion. It is a feature of the relationship between us and the universe, generated by our particular, limited vantage point inside a reality that, seen whole and sharp, does not flow at all. The tick you feel is real, but it belongs to the meeting of you and the world, not to the world by itself. Here is how it works. Imagine you divide the universe into two pieces. One piece is a clock, small and simple. The other piece is everything else, the rest of the universe. Now, in quantum mechanics, two systems can become entangled, their states woven together so that they are correlated in a particular way. Page and Wooters showed that if you entangle the clock with the rest of the universe in the right way, then even though the universe as a whole is sitting in a single, unchanging, timeless quantum state, An observer who looks at the relationship between the clock and the rest will see the rest of the universe changing as the clock advances. The whole does not move. But within the whole, the parts are correlated such that when the clock reads 1, the universe looks like this. When the clock reads 2, the universe looks like that. Time emerges as the correlation between the clock and everything else inside a cosmos that, taken all together, never changes at all. This is not just a thought experiment that lives on paper. In 2013, a group of researchers led by Ekaterina Moreva actually built a tiny laboratory version of this idea using entangled photons, particles of light. They set up a small quantum system to act as a clock, entangled with another system playing the role of the rest of the universe. And they found exactly what Page and Wouters predicted. An observer inside the system, using the clock, would see the other part evolving in time, changing, behaving as though time were flowing. But an observer outside the whole system, looking at it all at once, would see nothing changing at all, a static, frozen state. The flow of time was real from the inside and absent from the outside. The same physical situation was timeless when viewed as a whole, and full of flowing time when viewed as a relationship between its parts. Sit with what that experiment demonstrated, because it is one of the most quietly staggering results I know of. It means the flow of time you are feeling right now might be precisely this kind of thing. Not a river the universe is floating down, but a relationship between you, a tiny clock-like part of the cosmos, and everything else. The tick you feel is the correlation between your changing state and the changing state of the world around you, embedded inside a totality that does not tick at all. The philosopher Julian Barber pushed this picture to its furthest edge in his book, published in 1999, where he argued that time does not exist, full stop, and that what really exists is an immense collection of separate, frozen configurations, individual snapshots he called nows, each one complete and changeless. There is no flow connecting them. The powerful sense that one now leads to the next is, in his view, a kind of illusion assembled from the contents of each now, each snapshot containing within it what looks like memory and what looks like a record of a past, so that every frozen moment carries the feeling of having come from somewhere, even though nothing is moving. Let me try to put you inside this, because it is the strangest place we will stand all night, and feeling it is worth more than being told about it. Imagine the entire universe, everything that exists, laid out all at once as a single, immense, motionless whole. Nothing flows, nothing moves. There is no ticking clock hanging over it all, no master time counting the seconds, because the whole, taken together, simply is. And now imagine zooming in to one small part of it, to you, sitting where you are, and to the slice of the world immediately around you. From in here, from inside this one part, looking out at the rest, you see change. You see the world ahead of you and the world behind you. You feel this moment giving way to the next. You sense the steady forward pull you have always called the passage of time. And all of it, every bit of that flow, is the relationship between your part and the rest. A melody that exists in how the notes relate to one another, even though the sheet of music lies perfectly still on the stand. The flow is not the universe moving. It is the universe reading itself from the inside, one part registering another, and calling that registration now. If this is right, then the flow of time is something generated, not something given. It is produced inside a static whole, rather than being the stage the whole sits upon. And that means the question of what came before the flow of time is a question about the origin of something that, at the deepest level, was never truly flowing in the first place. There is a particular kind of intimacy to this unease that I find hard to shake. We are not talking about distant galaxies or the first microsecond of the cosmos anymore. We are talking about the thing you are doing this very instant, the experience of one moment becoming the next, and the possibility that this most immediate and undeniable feature of your existence is a manufactured effect, a relationship you are part of, rather than a current you are caught in. Carlo Rovelli, one of the architects of an approach to quantum gravity in which space and time are both emergent, has argued for years that at the foundation of the world there is no time, and that the time we know condenses out of thermodynamics and our own limited, blurred view of an underlying reality that does not flow, so we have now travelled underneath even the no-boundary pole. We have reached a place where time may not merely lack a first moment, but may not be fundamental at all, a feature that crystallizes out of a timeless, profound, the way warmth crystallizes out of cold molecules. And yet, and this is what makes the whole subject refuse to resolve, time is not symmetric. Whatever it is, however it emerges, it points, it has a direction. We remember the past and not the future. The river, real or generated, only runs one way. And that single stubborn fact, the directionality of time, turns out to carry a fingerprint of the beginning so specific, so fantastically fine-tuned, that it may be the closest thing we have to actual evidence about the edge of time. To read that fingerprint, we have to ask why time points at all. Part 10. The fingerprint in every memory. There is a fact about time so familiar that we almost never think to question it, and it turns out to be one of the strangest facts in all of physics. Time has a direction. It points. The past is fixed and the future is open. You remember yesterday, but not tomorrow. Cream stirred into coffee swirls outward and never gathers itself back into a neat white spiral. A dropped glass shatters and never reassembles. Everywhere you look, time runs one way only, from order toward disorder, from past toward future, and the one-way street feels as fundamental as anything could be. It is worth dwelling on just how unlikely a low-entropy beginning is, because the unlikeliness is the whole reason it demands explanation. Picture all the possible ways the matter and energy of the early universe could have been arranged. The overwhelming majority of those arrangements are disordered, lumpy, chaotic, already near the featureless equilibrium that disorder tends toward. Only a vanishingly tiny fraction of arrangements are smooth and ordered and low in entropy, poised at the top of a long slope with everywhere to fall. If the beginning had been chosen at random from all the possibilities, it would almost certainly have been one of the disordered ones, and a universe born disordered has no arrow of time, no history, no memory, no chance of cream ever being separate from coffee in the first place. The fact that ours began in one of the spectacularly rare ordered states is not something the laws of physics require. It is something they permit and do not explain, and it had to be true for anything like a past and a future to exist at all. This is why the arrow of time is, in a real sense, the most direct evidence we have about the beginning, more direct than any telescope. We cannot see across the Planck fog to the first moment, but we can see, in every cooling cup and every act of remembering, the consequence of how ordered that beginning was. The low entropy edge is not a hypothesis we cling to for lack of better ideas. It is forced on us by the simple, undeniable fact that time has a direction, and a direction has to come from somewhere. Whatever shape the beginning truly had, smooth pole or quantum bounce or timeless profound, it carried this fantastically improbable order, and you are feeling the proof of it right now, in the unbreakable difference between the past you can recall and the future you cannot. Here is what makes it strange. The fundamental laws of physics, the actual equations that govern how particles move and interact, do not care about the direction of time at all. If you filmed two particles colliding and bouncing apart, and then played the film backward, the reversed version would look just as physically legal as the original. The microscopic laws work equally well forward and backward. They are, in the technical term, time-symmetric. There is nothing in the basic rulebook of the universe that says which way is forward. And yet the world we live in is overwhelmingly, relentlessly, one-directional. How can a universe built from time-symmetric laws produce a reality where cream never unstirs and the dead are never young again? Where does the arrow come from, if not from the laws? The standard answer is the second law of thermodynamics, which says that a quantity called entropy, a measure of disorder, almost always increases. A neat arrangement, like cream separate from coffee, is a low entropy state, special and ordered. A mixed arrangement, cream blended throughout, is a high entropy state, disordered and overwhelmingly more common. Things go from order to disorder simply because there are vastly more ways to be disordered than to be ordered. So disorder is where any system tends to drift. That much is solid. But notice that the second law, by itself, only explains why entropy goes up from wherever it is now. It does not explain why entropy was ever low enough to have somewhere to climb from. If the universe had started in a high entropy, maximally disordered state, there would be no arrow at all, just a featureless equilibrium with no past and no future to distinguish. For time to have a direction, for entropy to have been rising for 13.8 billion years, the universe must have begun in a state of extraordinarily low entropy. It must have started exquisitely ordered. This is the part that points straight back to the beginning, and it has a name. Physicists call it the past hypothesis, a term given to it by the philosopher David Albert in the year 2000. The past hypothesis is the assumption that the early universe was in a very special, very low entropy condition, and it is doing enormous secret work. The reason you can remember the past and not the future, the reason the future feels open and the past feels settled, the reason anything ever happens in a particular order at all, traces back not to the laws of physics, which are indifferent to direction, but to that initial condition at the edge of time. The arrow you feel in every passing second was not built into the rules, it was built into the starting state. And how special did that starting state have to be? Roger Penrose tried to put a number on it, and the number is one of the most staggering quantities ever to appear in science. He estimated the precision required for the initial low entropy condition of the universe, the fine-tuning needed to set the cosmos up with an arrow of time pointing the way ours does, and he arrived at a figure of roughly 1 part in 10 to the power of 10 to the power of 123. I cannot write that number out for you, and neither can anyone else, because it is not just large, it is a tower of exponents. 10 to the 123 is already a 1, followed by 123 zeros, more than the number of particles in the observable universe. And the actual figure is 10 raised to that entire monstrous number. If you tried to write out the digits 10 per particle, you would run out of particles in the cosmos long before you finished. The ordered state the universe began in was special to a degree that strains the meaning of the word special. Now I want to draw the thread all the way back to where it matters most, to you, because this is where the beginning of the universe stops being a far-off abstraction and becomes something living in your own mind right now. The reason you can recall your childhood but cannot recall next week. The reason a photograph captures a moment that is gone rather than one still to come. The reason memory itself exists. The reason there is such a thing as a record, a trace, a history, the whole structure of remembering and anticipating that makes you a continuous self moving through your life. All of it rests on that fantastically fine-tuned, low-entropy condition at the edge of time. The asymmetry between your fixed past and your open future is a direct inheritance from the ordered state the universe was born in. The beginning is not safely 13 billion years behind you, sealed off and irrelevant. It is pressed into the structure of this exact moment, into the fact that you are remembering the start of this sentence and not its end. Let that settle, because it changes the whole meaning of the search we have been on. We have been treating the beginning of time as a remote destination, a place at the far end of cosmic history that we are trying to peer back at. But the beginning is not only behind you, it is inside you, in the direction of your thoughts, in the one-way flow of your experience, in the simple, miraculous, easily overlooked fact that you have a past you can remember and a future you cannot. Every memory you hold is a fossil of the low-entropy edge of time. Every time you feel certain that the past is done and the future is not yet written, you are feeling, directly, the fingerprint that the beginning pressed into reality. The edge of time is not far away. It is the reason this moment feels like a moment at all. And this gives us something we did not have before. It gives us a clue about the beginning that is not behind the plank fog, not hidden where our equations fail, but written plainly across the entire universe and across your own consciousness. Whatever the beginning was, whether it had a first instant, or rounded off like a pole, or emerged from a timeless profound, it carried with it a condition of extraordinary order, and that condition is real, measurable, and present in everything that happens. The beginning may not have been a moment, but it was, unmistakably, a boundary, a special edge that left its mark on all of time. A beginning does not have to be a starting gun fired at the start of a race. It can be a condition stamped into the structure of the whole, a fingerprint rather than a flash. The universe may have no first page, and yet every page carries the watermark of the edge. But I have been speaking this whole time as though the beginning, whatever its nature, was some kind of edge or boundary, even if a strange one. There is a serious body of thought that rejects even that. What if there was no edge at all? What if the universe did not begin in any sense, smooth or sharp, but simply continued, backward, through the moment we call the Big Bang, into something older? What if our beginning was not a beginning but a bridge? That is the last great possibility we have to face, and it replaces the vertigo of an edge with a vertigo of an entirely different kind. Part 11. Or maybe there was never an edge. Everything we have explored so far, even the strangest of it, has treated the beginning of the universe as some kind of boundary, a sharp singular edge in the old picture, a smooth rounded cap in the no-boundary picture, a place where emergent time bottoms out in the timeless picture. But a major line of serious work in cosmology refuses the boundary entirely and proposes something that sounds, at first, almost comforting and turns out to be just as dizzying as anything else tonight. The proposal is that there was no beginning, that the universe, in some form, has simply always been here, and that what we call the Big Bang was not a start, but a transition, a doorway from an earlier phase into ours. There is a genuine result that keeps the no-beginning models honest, and intellectual honesty demands that I put it on the table, even though it cuts against the comfort of an eternal past. In 2003, the physicists Arvin Borde, Alan Guth, and Alexander Vilenkin proved a theorem about any universe that, on average, has been expanding throughout its history. They showed that such a universe cannot be extended infinitely into the past. Its history, traced backward, must come to an end, a past boundary, in a finite time. The theorem does not tell you what happens at that boundary, whether it is a true beginning or a handoff to some other phase. But it does mean that the simplest dream of an eternally expanding past, with no beginning at all, runs into a wall of its own. Some of the bounce and cycle models are carefully built to avoid the theorem's assumptions, by having the universe contract before it expands, but the result stands as a warning that abolishing the beginning is harder than it first appears. So even the escape route of an infinite past is not a free one. You can build a universe with no first moment, but you have to pay for it, with a contracting prior phase, or a cycle, or some structure exotic enough to slip past the theorem. There is no easy version where the universe simply always was, expanding placidly forever backward, no questions asked. Every road we have, the smooth pole, the timeless profound, the springy bounce, the endless cycle, costs us something, takes away some piece of the simple story, and leaves us holding a stranger one. The universe seems determined to deny us a comfortable beginning, and equally determined to deny us a comfortable absence of one, and that double denial may be the truest thing we can say about the edge of time tonight. The most developed version of this comes from an approach to quantum gravity called loop quantum cosmology. Recall that general relativity, run backward, predicts a singularity at the beginning, an infinitely dense point where the theory breaks. Loop quantum cosmology applies quantum principles to the geometry of space itself, and when it does, the singularity changes character. As the universe is run backward and the density climbs toward the Planck scale, the quantum nature of space produces a powerful repulsive effect, a kind of pressure that switches on only at unimaginable densities and pushes outward hard enough to halt the collapse. Instead of crushing down to an infinite point, the contracting universe reaches a maximum density and then rebounds. The Big Bang becomes a big bounce, and on the far side of the bounce is not nothing, not a smooth pole, but another universe, an earlier cosmos that had been contracting, falling inward until it reached the bounce and became ours. In this picture, time does not begin at the Big Bang. It runs straight through it, backward into the previous universe, and presumably backward through whatever bounce began that one, and on and on. There is no first moment, because there is no edge. The past simply continues, possibly forever, an endless chain of universes, each born from the collapse of the one before. Roger Penrose, the same physicist who calculated that staggering low entropy number, reaches a similar non-beginning by an entirely different road in his conformal, cyclic cosmology, stringing together an infinite sequence of cosmic eons, each one's distant, cold, empty future, becoming the hot, dense birth of the next, a cycle with no first link. Let me take you into the bounce, because it is the mirror image of everything we felt at the pole, and the contrast is the whole point. Imagine riding the universe backward again, as we did before, but this time in a cosmos that bounces rather than caps off. You fall inward, everything contracting around you, galaxies streaming together, the heat rising, the density climbing, and ahead of you looms the moment everyone calls the beginning. You brace for the wall, for the pole, for the place where time runs out. And then, at the last instant, at the very bottom, the wall is not a wall, it is a floor, and the floor is springy. The contraction reaches its limit and reverses. The density crests and falls, and you find yourself rising again on the other side, the universe expanding around you once more. But it is not our universe. It is an older one, running in reverse from our point of view, a whole cosmos that lived and contracted and fell to this point to become the seed of everything we know. There was no edge to fall off. There was always more. Behind the beginning was another beginning, and behind that, another, with no first one anywhere in the infinite regress. This is the opposite vertigo, and I want to name it clearly, because it is just as unsettling as the empty pole, only in reverse. At the pole, the terror was that there might be nothing before the beginning, no first page, the book running out at its own edge. Here, the terror is that there might be no beginning at all, an infinite past, an endless chain of universes, stretching back with no first link, no origin, no answer to where did it all come from, because the chain has no end to grab. Both possibilities take away the simple story we started with, the story of a single, clean beginning, a moment when everything switched on. One takes it away, by dissolving the edge into a pole where before stops meaning anything. The other takes it away by removing the edge entirely and handing you an infinity instead. I have to be honest about where the science actually stands among these options, because the honesty is the most important thing I can give you. We do not know which of these is true. We do not have the data to decide between an edge that rounds off smoothly, an edge that was never an edge because time is not fundamental, and a time that simply runs backward forever through bounce after bounce. There are even more exotic possibilities I have only gestured at. Models in which two arrows of time run in opposite directions away from a single central low-entropy moment, so that what we call the beginning sits in the middle, with our universe running one way and another universe running the other, and no true past at all. The frustrating, magnificent truth is that all of these are live, all of them are taken seriously by serious people, and the beginning of time remains hidden behind the same fog at the Planck scale that has stymied us from the start. Each model is a different guess about what shape time takes inside that fog, and we cannot yet see in to check. So we arrive, after all of this, not at an answer, but at a transformed question, and I think that transformation is the most valuable thing this whole journey has to offer. We started with a question that felt simple and obvious. What was there before the Big Bang? And we are ending somewhere that question can barely be spoken, because nearly every word in it has come loose. To gather everything we have found, and look at it all at once, to feel the full strangeness of where the physics has left us, we need to stand back and ask not what came before time, but what we have actually learned by discovering that the question may have no meaning. That is where we are going to end, with the most honest question we have ever asked. Part 12. The most honest question we have. Let me gather the whole journey into one place, because we have travelled a long way from the simple question we started with, and it is worth seeing all of it at once. We began with what felt like the most natural question in the world, the one everyone eventually asks. What was there before the Big Bang? And layer by layer, that question has come apart in our hands, not because we failed to answer it, but because we kept discovering that it was not the question we thought it was. I find it worth pausing on how rare it is, in any part of life, to be handed a question this clean and this honest. Most of the questions that haunt us are tangled up with things we want to be true, with fears and hopes that bend our reasoning. But the question of whether time had a beginning is almost pure. It asks for nothing, promises nothing, flatters no belief. It simply stands at the edge of what can be known and waits. And the people who have taken it most seriously, from a bishop in late antiquity to the physicists filling chalkboards today, have all been changed by it in the same way, brought to the same humble posture, the recognition that the universe is not required to be the size or shape of our intuitions, and that some of its features may lie permanently just past the reach of the minds it happened to produce. At the surface, we found that before the Big Bang assumes a stretch of ordinary time running backward past the beginning, and that this assumption is almost certainly the wrong one, the way assuming a road continues north past the North Pole is wrong. One layer down, we found that the real question is whether time itself had a first instant, and that our best theory of the beginning, general relativity, does not answer it but breaks at it, predicting an infinity that marks the edge of its own validity. We found that the philosophers saw the trap centuries ago, that Kant could prove time began and prove it could not, and that Augustine, 1600 years back, already suspected there was no then when there was no time. We walked to the Planck scale and watched the very idea of the next moment dissolve into fog. We followed Hartle and Hawking into imaginary time and watched the dimension of time round off into space, so that the beginning became a smooth pole with no edge, and before ran out the way south runs out at the bottom of the world. We went underneath even that and found an equation for the whole universe with no time in it at all, raising the possibility that time is not fundamental but emerges, like warmth from cold molecules, from a timeless, profound. We saw time reappear as a relationship between a clock and the rest of a frozen whole. And then we found, in the simple one-way flow of our own experience, the fingerprint of a beginning fine-tuned past all comprehension, a boundary that may not have been a moment, but left its mark on every memory we hold. And finally we face the possibility that there was no edge at all, that the universe bounces or cycles backward forever, with no first link anywhere. So what do we actually know after all of that? We know the universe has been expanding and cooling for about 13.8 billion years, and we know it with great precision. We know that running it backward leads to a state of enormous heat and density, and that our theory of that backward journey works beautifully until the last sliver of a second, and then fails. And we know that everything past that failure, the true nature of the beginning, whether time had a first moment, whether time is even fundamental, whether there was an edge or no edge at all, lies behind a wall of physics we have not yet built. We can run the universe back to a fraction of a second after the apparent beginning, and we cannot say whether time began, emerged, or never started. That is the honest state of human knowledge, and I think there is something magnificent in being able to say it plainly. I want to return, at the end, to the image we have circled all night, because it has changed its meaning along the way. When Hawking said that asking what came before the Big Bang is like asking what lies south of the South Pole, it sounded, the first time, like a clever way of avoiding the question. By now, I hope it sounds like something else. I hope it sounds like a genuine possibility about the shape of reality, that before is a direction that runs out, that the universe may be finite in its past, and yet have no first moment, no edge to stand before, no empty waiting room where nothing had yet begun. The question we started with may have been pointing at nothing the whole time, not because the universe is hiding something, but because the words we were using describe a place that the geometry of time does not provide. And I keep coming back to Augustine, candlelit, 16 centuries ago, writing that there was no then when there was no time. He could not have known about imaginary time, or the Wheeler-DeWitt equation, or the entropy of the early universe. He had no telescope, no mathematics of curved space-time, nothing but the relentless honesty of a mind willing to follow a question past the edge of comfort. And he arrived at the same place our most advanced physics keeps arriving. There was no then. The question of before may dissolve, not into an answer, but into the quiet recognition that it was never quite a question. We have spent 100 years building the instruments and the equations to test that ancient intuition, and what we have found is that we still cannot see across the fog, but we can see, more and more clearly, that the far side may not be shaped like anything we expected. There is a particular quiet that comes over me whenever I follow this question all the way to its end, and I suspect you may feel a version of it now. It is not the quiet of disappointment, of having looked for an answer and come back empty-handed. It is closer to the quiet of standing somewhere very high and very still, where the ordinary noise of certainty falls away, and you can finally hear how large the unknown actually is. We are small, time-bound creatures who learn to ask about the beginning of time, and the asking carried us further than anyone had any right to expect, all the way to the edge of what thought can do. That we cannot see across that edge is not a defeat. It may be the most accurate thing we have ever discovered about our place in the order of things, and maybe that is the real gift hidden inside this question, the reason it is worth spending a long, slow night on. It takes the thing we are most sure of, the steady forward march of time, this moment giving way to the next, and it shows us that even this, even the ground floor of all our experience, opens onto mystery when we look hard enough. The flow you are riding right now may have had a first instant, or rounded off into a pole, or emerged from a stillness underneath, or run on forever with no beginning at all. You are living inside the very thing whose origin we cannot name. And there is something steadying, rather than frightening, in letting that be true, in setting down the need for a tidy first page and simply resting, for a while, in the enormous open question of being here at all. So here is where I will leave you tonight, drifting at the edge of time. The next time that old question rises up in you, late at night, the one about what was there before it all began, I hope you will feel it a little differently. Not as a question with a missing answer, a gap waiting to be filled, but as something stranger and more wonderful, possibly the most honest question we have ever asked, a question that has taught us more, by refusing to be answered than most answers ever could. Maybe time had a first moment, and we will someday find it. Maybe time rounds off into a pole with no first moment at all. Maybe time is not even the fundamental thing, and the flow you are feeling right now is something the universe generates from a stillness underneath. Or maybe there was no beginning, only an endless past we will never see across. We do not know. And in that not knowing there is no emptiness, only an opening. The same opening a bishop felt 1600 years ago, and the same one the equations feel now, the sense that we are standing at the edge of something the mind was never built to hold, looking out, for as long as we can keep our eyes open, into the place where before quietly stops, and wondering.